So at the end of the day, you need to understand how the word and sentence vectors have evolved over time, how the algorithms have evolved, etc. And all you need to have most of the time is to have a strong understanding of the pros and cons of each of the word or sentence vector algorithm and use them accordingly. And on any day when you need to know more, you can go and delve deeper into a particular algorithm to make any changes, etc. But from a practical applied NLP standpoint, if you just have a good baseline understanding of TF-ID of word to vec and all the variants up to sentence transformers, that's good enough. So let's just see how word or sentence vectors have evolved over time. So in the first category, we have TF-IDF, which falls into the category of sparse embedding. And we know that word to vec attempted to solve this sparse embedding problem by providing a dense embedding because of its training strategy that involved training a neural network algorithm with corresponding surrounding words around a given word. With that, we were able to put together similar words in a closer embedding space. So the vectors for similar words are close together. And because of the power of dense embedding as well as vectors being close together, whatever real world operations that we can think of, we are able to kind of emulate them in the word vector space as well, which is king minus man plus woman is equal to queen, as well as any noun comparisons. For example, plural of mouse is mice. Similarly, elephant is elephants, etc. So you can do comparisons like mice minus mouse plus elephant is equal to elephants, etc. And we have seen the problem with word to vec, which is it cannot differentiate between different senses of a word. For example, between computer mouse and the house mouse. And also we have seen that when it comes to sentence embedding, we are just averaging out the individual word vectors. So there is no weightage or importance given to certain keywords, etc. And the next evolution from word to vec is actually sense to vec. So during training, what we can do is we can append each word with its corresponding POS, parts of speech, or NER, named entity recognition tag. What I mean by that is, let's say you have a word like bank. Bank could be a verb. Bank could be a noun, financial bank, whereas verb could be like depend on somebody, banking on somebody, etc. So in such cases, all you can do is, in the context where bank is verb, you can replace bank by bank underscore V. And in the context where bank is noun, you can replace bank underscore N. And you can train a word vector algorithm, parts of speech appended entities, so that when during query time, when you give bank underscore N, instead of getting depend and other things as the near word vectors, you will mostly get financial bank related word vectors like loan, etc. That's what you can do. So sense to vec is actually an improvement over word to vec, where you can actually append the sense of a given word even. And also you have seen that to counter out of vocabulary words, we have fast text, which can divide a given word into its subtokens. Again, sense to vec is limited because when you take the case of mouse, mouse is a noun in both computer mouse as well as the house mouse. So you cannot really differentiate with the parts of speech tag. The other thing that you can do is give a named entity recognition NER tag as well appended to it. But like I mentioned, still it has some shortcomings. So over TF-IDF we have word to vec, and over word to vec we have sense to vec. But still we do have some issues which are, one, we are unable to fully resolve the context of a given word. So we are unable to do word sense disambiguation. So we still need contextual embeddings. Secondly, we don't really have word importance captured because we are still doing lookup for a given word and getting its word embedding. And when you're getting sentence vector, you're just plainly averaging the word vectors, whereas we want to also calculate the importance of a given word. So we want to change the weights, or we want a single word to have more context and its embedding should come from context across the words that are surrounding it. And Elmo and Bert fall into this category of contextual embeddings. So essentially, if you give a sentence, for example, I am going to the bank to deposit some money, in that case, automatically the word bank will have a different word embedding when compared to another sense where I am going to the river bank. In both the sentences, bank is a noun, but since the context is different, you'll have contextual embeddings because of algorithms like Elmo and Bert, etc. For simplicity, you can think of Elmo as the first contextual embedding that came out, which tried to solve this word sense disambiguation problem that you had with mouse, bank, etc. And then came algorithms that specifically focused on sentence to vec approaches. We just realized with word to vec that although we are able to get the perfect embedding for a given word, just averaging the word vectors of words in a given sentence and getting a sentence vector doesn't really suffice, because plain averaging doesn't capture the complete picture of a sentence, whereas we should be able to do some smart averaging across the word vectors of individual words in a sentence. So in order to solve that, several algorithms like skip thought vectors, infercent, and universal sentence encoder came into existence, which is instead of dealing on a word level, they directly deal on a sentence level to give a unique vector for the whole sentence such that similar sentences are closer together. And these algorithms, skip thought vectors, infercent, universal sentence encoder, most of them used RNN, recurrent neural networks like LSTMs and GRUs, in order to generate these sentence embeddings. Of course, universal sentence encoder had a variation which used transformers, which is the advanced algorithms that captures relationships among different words in order to get an embedding for a given word. And moving further on, current state of the art is actually sentence transformers. So these are transformer based algorithms that are trained on top of BERT, etc. to encode sentences specifically to keep similar sentences closer together in the vector space and dissimilar sentences farther together in the vector space. So they are fine-tuned on top of BERT-like algorithms to produce high-quality sentence embeddings. And one thing to remember is that not only words or sentences or paragraphs are converted into vector, even images could be converted into vectors. So there are models like CLIP and several vision algorithms that can convert a given image into a single vector of fixed dimensions so that you can compare images among each other, etc. So if you come to sentence vector improves on top of the word vector. So you can see that the biggest shortcoming of word to vec was there was no word sense disambiguation. Secondly, the average vector was pretty simple, just averaging across all the words. So sentence vector essentially solves that problem, where although it is termed as sentence vector, you can just give an individual word or just a phrase even and get vector out of it. For example, you can just give a single word like Batman and get a vector, or you can give multi-word like Donald Trump or Joe Biden, etc. and also get a vector, or you can give a sentence and a whole paragraph and get a vector. So at the end of the day, again, just like word to vec, sentence vectors, that is sentence transformers, can convert a single word or just a phrase into a vector directly of 768 dimensions. And again, a sentence could be converted into a single vector of 768 dimensions. The only difference is that in word vector algorithms, we just averaged out all the individual word vectors in a given sentence. Whereas when it comes to sentence vectors, what happens is that, for example, a given word like directed does not independently have a vector of its own. Rather, the directed vector comes from a combination of all the surrounding words to the left and right of this. So you can kind of imagine that whatever we wanted to do, which is smart weighted averaging of word vectors in word-to-vec algorithm, we kind of do that in sentence transformer inherently, where each individual vector that we get is actually a smart weighted combination of other vectors. And at the end, we also average out all the vectors that we have in order to get the single smart vector. But remember that in word-to-vec, we have kind of a lookup table scenario where individual word and its vector is obtained. Whereas in this case, this individual vector is not pre-calculated and kept in a lookup table, but rather generated dynamically depending on the sentence. So that vector is very efficient and it captures all these complexities like word sense disambiguation, like mouse in both cases, as well as the relationship of that word with respect to the corresponding words that are to the left and right. So you can assume that unlike word vectors, this is a smart vector that is of 768 dimensions. Similarly, for paragraph also it's the same. We essentially have a max length, usually 1024 tokens or tokens converted to some word count like 512, etc. So sentence vectors, etc. can take, let's say, a paragraph of maximum 500 words, etc. and it can generate a smart vector even. So at the end of the day, a word is represented by a single vector. A noun phrase or verb phrase that is multi-word is also represented by a single vector. A sentence is represented by a single vector. A whole paragraph or document is also represented by a single vector. So now you can do easy comparisons among each other. So just to recap everything that we have learned, we have TF-IDF for high-level document comparisons and classifications as well, but it has quite a few shortcomings. One is there is no word similarity that is embedded. Second is the vectors are very sparse. Most of them are zeros. So we moved from that to dense vectors. That is, instead of having 50,000 length, we have now 360 dimensions or 768 dimensions length vector. So word-to-vec was one such algorithm. In order to tackle subwords, we have fast text. And in order to have word sense disambiguation, we introduced sense-to-vec. And beyond that, we have ELMO, which actually gives contextual embeddings and performs better than sense-to-vec. So I just kept all of these algorithms from word-to-vec to ELMO in these dense word vectors because each of them improves over the other by solving some of the shortcomings of the before one. Now, we realize that just getting vectors for word isn't sufficient. We need to do better, that is smart averaging, to get a sentence vector, because a sentence vector is not just plain averaging of individual word vector. We need to have some kind of weight or importance factor also captured in the sentence vector when we are getting the combined thing. So these algorithms like skip thought vectors, InferSent, Universal Sentence Encoder, USE, improved on word vectors and tried to get us sentence vectors or document vectors straight away that are of higher quality that we can use for comparisons. But still they had some shortcomings in the sense that the vectors are not of high quality and Then came sentence transformers, which is based on transformer based algorithms for sentence vectors. Although it is called as sentence vector, it can take a single word or a multi-word phrase or a sentence or a document and generate vector, single vector of, let's say, 768 dimensions. And this is currently the state of the art, the sentence transformers and its variants. And they are the ones that are used in cutting edge state of the art projects, NLP projects. So the practical guide is that if you are doing lightweight classification or high level comparisons, you can use TF-IDF vectors if you have a lot of corpus. If you don't have the corpus and you want to do again lightweight classification and comparisons with dense vectors, you can go for word2vec because you don't need to have any corpus or pre-train anything. So averaged word vector and doing classifications or comparisons is a good baseline. But if you really want to hit it out and get state-of-the-art accuracies, you can use sentence transformers. And the power with dense embeddings is that even if you have 1 million or 10 million documents, you can just convert each of the document into a single vector using sentence transformers, and you can place all those 1 million or 10 million documents in a vector database that is specifically designed for comparing vectors among each other. Now let's say you have a new movie plot or new document, you can convert that into a vector and do very fast comparisons across all the 1 million or 10 million documents that you have, comparing the vectors to fetch the most similar vectors, etc. So essentially, remember this thing. If you don't want to do heavy computation and want to do something very quickly, you can use pre-trained word2vec algorithm and just get your embeddings and average embeddings and do comparisons. That's rule number 1 to remember. Rule number 2, if you want to get state-of-the-art accuracies, go for sentence transformers. Thanks for watching.